Convolution products, an interesting product that is heavily used in engineering. You know, mathematicians like to push the boundary, and they often do, but they do with caution. They're not stupid. They know when to press and when not to press. I remember several years ago, I was just slightly older than you, and I took what they call the Putnam exam. It is an exam given to undergraduate students, to a select few from schools from around the nation. And one of the questions they asked us was, as you know, if you have two functions fg, and let's say you have a product of those two functions, the derivative of the products is this, right? And the question on that exam was not that you should find two functions that obey this rule. That would be an easy one to handle. The question was find all functions f and g such that fg prime is f prime g prime. Okay, you should look into it. It's an interesting problem. Similarly, when we dealt with linear ODEs, if you remember lately, we had a 3-step process on how you solve ODEs. You're given an initial value problem. Remember, it cannot just be an ODE. You need initial conditions. And the steps we took were we applied Laplace on both sides of the equation. We split the algebra because it turned out to be an algebraic equation in terms of S, right? We split it using partial fractions almost all the time. And then we worked backwards by applying inverse Laplace. It's a one-to-one function, so it's okay to apply inverse Laplace of some function of S, like this one. You remember this one gave us 1, right? And that gave me the solution to my initial value problem. And the example I wrote here, on my third step, you'll get something like this. At least one of the terms would look like this, and you'll know that this is Laplace, inverse Laplace of 1 over S, which is just 1, because Laplace of 1 is 1 over S. And you might have an initial value problem where you come down and you come up with some algebraic equation, and now you're trying to find the inverse Laplace of this quantity. And of course, you all know what to do. You split this into something like this. And so on and so forth, right? But you might be tempted to split it this way, incorrectly. You might be tempted to do this. Inverse Laplace of 1 over S times inverse Laplace of 1 over S squared plus 1. And the reason you might be tempted, it's not because you think inverse Laplace of a product is the product of inverse Laplace. This is completely false, okay? Because you're familiar with inverse Laplace of 1 over S, and you say, okay, well, I know the answer to that one. That one is 1. And this is also a famous expression that should give me sine of t, right? And of course, if that is true, this is true, definitely true, but this is not true. In fact, if it was true, then Laplace of sine t, then Laplace of this product 1 times sine t, which is exactly Laplace of sine t, right? Because 1 times anything is the same thing. But we know for a fact that that is 1 over S squared plus 1, which is different from 1 over S times S squared plus 1. We're missing an S. So clearly, inverse Laplace of a product, think of this as a product, 1 over s times 1 over s squared plus 1, is not inverse Laplace of 1 over s times the inverse Laplace of the other factor, and hence my points. So mathematicians thought to themselves, like, okay, is it possible to have inverse Laplace of a product, like 1 over s times 1 over s squared plus 1, and get inverse Laplace of each factor? Of course, we know it's false. I just gave you an example, which is a great counterexample to say that you can't do that. But is there such a product, some unique product, not necessarily the multiplication that we know, but some convoluted product? The answer is yes, and that's the beauty. And I put it in green so that you don't think it is the typical multiplication, okay? And that is essentially what we want to be able to do. Wouldn't you love to split inverse Laplace of some ugly products into inverse Laplace of each piece? And if you have 3 ugly products, you split it into 3 parts? I mean, it would be really cool. Of course, we know that it is not true for typical multiplication, but for some other unique product, it is true. So, and that's all we want to do today, is discover what kind of convoluted products would let you obey this rule. And that, hence, introduction. So, we are going to begin with the typical definition of Laplace transform. Laplace transform of little f is this, which happens to be capital F of s. Just by definition, this is Laplace of a little f. Okay? And we're going to define g of s to be Laplace, to be the integral of this quantity. As you can tell, this is Laplace of little g of t or v or whatever. I didn't want to use u because I need 2 letters, so I used u and v. Okay? This is just definition of Laplace. And we're going to look at the products, because I'm trying to eventually get to here and figure out what is this product that will allow me to go from here to here or vice versa. So if you multiply f of s by g of s, you're just going to multiply this quantity by that quantity. These are functions, okay? Nothing to it, okay? This is like 3rd grade. Now, if you look here, this is a function of v. This depends on v. So as far, this is a constant as far as v is concerned. Imagine v lives in this world of v's and doesn't recognize u as a variable. So as far as v is concerned, this is just a constant. So I can take this entire quantity here and dump it right there in front of e to the negative sv. That's all I did. I took it inside, okay? So everything remained. That is just a typical product, normal product, so multiplication is commutative. I just left this with this stuff, and I left this with this stuff, and I took all of this and I dumped it inside. And I put it in blue brackets so you could see it. Now, you know how to use double integration. You start with the inside and then you go and you work your way out. So this is the integral from 0 to infinity, and because v is the last one, I wrote v so I don't confuse you. So v goes from 0 to v approaching infinity, and this is u, letter u, not u, y-o-u. Letter u goes from 0 to infinity, okay? And since multiplication is commutative, I just combine these two like this. I pulled out the negative s. We've done this a few times now. fu gv, here it is. Now, of course, du, dv have to remain in the order that is written. It's okay to commute g of v with f of u, right? Or commute these two, but it's not okay to commute these. If we write this as dv du, we have to change the limit of integration, as you know, from multivariable. So that's all I did. So e to the negative su, e to the negative sv gave me this. F at u times g at v du dv. Now, I'm going to let t be u plus v. So it's easy to recognize that this is e to the negative st. Okay? I'm going to leave v alone, but I'm going to replace a letter u by t minus v. Okay, u is t minus v. I'm going to leave v alone. I'm going to replace u by t minus v. So this is f of t minus v, g of v. I like v, so we're going to keep v. I could have kept u, but I decided to keep v. Du is dt. That doesn't change. And dv remains. Now, yes, so I am here. And these are, I made a mistake here. Okay, yeah, let me see what I am. Yeah, I made a mistake here. So this is u. Oh, no, I didn't. So dv, so v, the limit of integration didn't change. V from 0 to infinity, 0 to infinity. However, u went from 0 to infinity. When u was 0, t will be v. So I change. Now the limits of integration here are corresponding to t. So t has to go from v to infinity. Instead of from u equals 0, you're going to have t equals v. Okay, so this is correct. Now, what I'm going to do next, I'm going to change the order here, which means I hope you could just draw a little, what is it called? A TV plane, and figure out if t goes from v to infinity and v goes from 0 to infinity, why is it true that t will go from v to infinity and v will remain from 0 to infinity, okay? So just do a little table, basically a TV plane, and let t go from v to infinity. That's just a line like y equals x to infinity, and v goes from 0 to infinity. And flip the order as you've done many times in calculus and multivariable calculus and see if this is true, okay? So remember, I'm still looking for the product of f times g, capital F times capital G, all right? So now, what I'm going to do next is I am going to move this e to the negative st right there and integrate basically this piece. The integral of this times that, I put it together. I didn't change anything except that since multiplication is commutative, I moved the e to the negative st right next to dt. Okay, everything remains the same. Now, we're going to call, for simplicity, we're going to call this integral h of t. Okay, so f of s times g of s equals the integral from 0 to infinity, h of t, which is this integral in green, e to the negative st dt, which is precisely Laplace transform of h of t by definition. Isn't that true? In other words, f of s, g of s is Laplace transform of h. What is h? H is this integral. Now notice that this integral involves f and g, and that is a normal multiplication right there. Now the input is not the same. This has v and this has t minus v, and that's important, okay? So I went down here, and we are going to define this integral, which we call the h of t, as f dot g in green of those two functions, because this integral involves function f and involves function g. You couldn't call this, obviously, you couldn't call this fg. That's not true. This is not fg. That's the integral of f times g, and their inputs are different. And that's why we introduce a difference, t minus v here. We introduce a different product, okay? So we are going to define the convolution of f star g as this. This is your h of t basically. But this h of t does involve function little f and function little g. So we're going to define this product in this format. So remember, f of s times g of s is Laplace of h of t. So if we define this integral as f star g, then clearly capital F of s times capital G of s is Laplace of little f star little g. So this is how we are going to define that product, which will enable me, as you will see, to write Laplace inverse of fs, fg, as Laplace of each, okay, as you will see in a minute. Okay, so remember, we are here. We have just found f of s times g of s to be this function, which we called it the convolution of f and g, right? The convolution of f and g. I should say Laplace of that because we called h of t is just this quantity here. So the integral of h of t is Laplace of h. So therefore, f times g is Laplace of h, which is Laplace of little f star little g. Now, by definition, f of s is Laplace of little f, and g of s is Laplace of little g. So, Laplace of f star g, which is this, is f of s, g of s. But f of s is Laplace of f of t. I just called it f. And g of s is Laplace of little g, or g of t. So here you go. Laplace of f times Laplace of g is Laplace of a product, but it is a unique product. It's not the products we're familiar with. Therefore, we know, look here. If I apply inverse Laplace, look at this, okay? Capital F times capital G is Laplace of little f, little g. Therefore, little f, little g, I'll write it. Little f star little g is inverse Laplace of f of s, g of s. Isn't that true? According to this. So little f, little g is inverse Laplace of f, g, capitals, right? Now, so inverse Laplace of this is just a little f, little g. But what is little f? Little f is inverse Laplace of capital F. And little g is inverse Laplace of capital G. And hence, what we were trying to achieve. Because if you are solving initial value problems, always, often, and always, the hardest step is step 3. Because to find inverse Laplace of some quantities are nice, like this one. Some quantities are not nice. And even if they're nice, to use partial fractions can make things very, very messy. And the hope is it possible to split this product, 1 over s times 1 over s squared plus 1, as Laplace? Is it possible to split it like this? That's the question. And the answer is yes, so long this product is not the typical product, but it is the convolution product, which is defined by this. Okay? So the convolution product of f and g is denoted f star g, and it is defined exactly this way. So if you want to know what the heck is this product is, it is this, okay? Notice they involve both functions f and g, and notice also that the input is not the same. There is a little translation g of x, if you have f of x and you have g of x, you find g of negative x, which will move g across the y-axis, and you start moving it along some t. Imagine t is 0, so you just don't move it. And as t increases, g of negative x or g of t minus x keeps moving toward f of x. So these are totally different functions that are only going from 0 to t, okay? Because that's what we got here. When we defined h of t, which we called f star g, goes from 0 to t. It's not from 0 to infinity, okay? Keep that in mind. So this is the definition of the convoluted product, which enables me to write this if I care, or to write this if I care, okay? Now we know Laplace and inverse Laplace are linear operators. So Laplace of a sum is the sum of Laplace. Inverse Laplace of a sum is the same thing. Same thing with a difference, because a difference is no more than a sum, okay? So we know it is true with addition and subtraction, and the question is, could you use it for the products? Laplace of the product is the product of Laplace, and inverse Laplace of our products is the product of the inverse Laplace. The answer is yes, so long you use the convoluted product, not the typical products that we know, okay? And I have already given you an example where the typical product would never do it. You remember you got 1 times sine of t. So inverse Laplace of 1 over s squared plus 1 is not inverse Laplace of 1 over s times inverse Laplace of 1 over s squared plus 1, unless that product is the convoluted product. And that's the key to this presentation today. I hope, I know I introduced a lot of notation here. Just go through it slowly and don't rush. Make sure you are convinced, especially, by the way, of how I moved. I interchanged the limits of integration, right? dt, dv, I called it dv, dt. Make sure you know how to move these limits into these two limits. I know you've done it many times. Just make sure you're true to yourself when you go through this. The last thing I want to mention very briefly is what do we define to be nice functions? And f and g are nice functions if they obey this rule, that Laplace of a product with the convoluted product is the product of Laplace, the typical product of Laplace. This is just a theorem which can actually be proven very easily. This is just definition. We don't prove definitions, as you know. Your parents didn't have to prove to anyone why they decided to call you by your first name. That's just so we can communicate. So we don't prove definitions, but definitely we can talk about this theorem next time if we have some time. All right, take care.